In this video, we're going to talk about the definite integral and some of its properties. So we're going to start out with the definition. So to start off, we have a function f. This function needs to be defined on the closed interval from a to b. We're going to create a partition into n pieces. Each piece has size b minus a over n, which we call delta x. Our partition consists of the points x0, which is a, x1, which is a plus delta x, xi, in general, is a plus I times delta x, and ends with xn, which is a plus n times delta x, which is just b. These points in pairs define subintervals. The first subinterval is I1, which goes from a to x1. I2, the second subinterval goes from x1 to x2, and all the way down to the final nth subinterval, which goes from xn minus 1 to b. On each of these subintervals, we're going to choose a sample point. x1 is some number between a and x1. x2 star is some number between x1 and x2. And finally, xn star is some number between xn minus 1 and b. We call these sample points, and we choose one from each of the n subintervals. So the definite integral of f from a to b, which is expressed as this symbol here. So we have our starting left endpoint a, our ending right endpoint b, this elongated s, which is the integral sign, f of x, and then this dx. dx indicates which variable we are using when we integrate our function f. It's defined to be the limit as n goes to infinity of the sum from I equals 1 to n of f evaluated at xi star multiplied by delta x. Just like when we were talking about the right endpoint Riemann sums, each of these terms in this sum represents the area of a rectangle. The width of our rectangle is delta x, and the height of our rectangle is given by plugging the sample point xi star into our function. The sum of each of the areas of these rectangles gives us an approximation to the region bounded by y equals f of x, the x-axis, the line x equals a, and the line x equals b. Taking the limit gives us the actual area of the region enclosed. Now, provided that this limit exists and gives the same value for all choices of sample points. If this limit does exist, we say that f is integrable, and we specify where it is integrable, because not all functions will be integrable on all intervals. So we say that f is integrable on the interval from a to b. So each of the pieces in our integral has a name. We call the function that's being integrated the integrand. We call the number on the bottom of the elongated s, a, the lower limit of integration, and b is the upper limit of integration. So the condition that this limit of a sum has to not only exist, but exist for all possible choices of sample points and give the same value for all possible sample points is a pretty big condition. It turns out that for continuous functions, or functions with only a finite number of jump discontinuities, our function is always integrable. This theorem says that if f is a sufficiently nice function, where sufficiently nice means either continuous or has only finitely many jump discontinuities on an interval from a to b, then f is an integrable function. So we should note here that there's a nice consequence of our extraordinarily general definition for the definite integral. So if you mix together the theorem here and the theorem here, then you can see that as long as your function f is sufficiently nice, where that means either it is continuous or it only has finitely many jump discontinuities on the closed interval from a to b, then we can always compute the integral from a to b of f by computing the limit of the right endpoint sums. So now that we know how to compute the integral for some nice continuous functions, let's think about some properties of the definite integral.